Hello students. In this recording, I will discuss regarding IEEE 802.11 project that is regarding the wireless LAN, also known by the name Wi-Fi. So that standard we will discuss in this lecture. So while discussing its architecture, so the standard defines two kinds of services, the basic service set and the extended service set. So we'll discuss about the basic service set BSS and the extended service set ESS. So that is the part of architecture. It provides two type of services. Then we will discuss regarding the MAC layer. Particularly the focus would be on distributed coordination function, which will use CSMA-CA as an access mechanism. And then there is a polling mechanism as well, which comes under the point coordination function, which is also the part of MAC sublayer, but occasionally being used. Mostly we rely on distributed coordination function, then fragmentation, and probably in the next lecture or so, or maybe in this, we'll discuss about the frame format and the frame types. That is all. We'll discuss about the wireless LAN, and there we'll stop. So here we will see the basic service set. So there are two requirements. One requirement is that you require a LAN for yourself. You don't want to connect yourself with outside world. So the hosts which are the part of your LAN, you don't want those hosts to get connected to the outside environment, to the outside environment, to the outside internet. In that situation, it doesn't require an access point, and all other nodes are self-configured. They can easily contact other nodes which are the part of the same basic service set. So that doesn't require any link. That doesn't require, because the medium is in itself is a facilitator for their communication. So that is the ad hoc environment, that is the ad hoc BSS, because there is no infrastructure. Another name for this is infrastructure less basic service set, which doesn't require any infrastructure, because infrastructure you do require for gluing your environment, for gluing wireless environment with a wired environment, because the outside environment is wired, internet is wired internet. So you get yourself connected with the outside environment. In that situation, you require something to get the environment glued with the outside environment. So for that purpose, we have an access point. Already we have discussed about the access point. It is never get yourself confused with the switches, that as in case of wired internet we have switches. In case of this wireless LAN we have access point. It is not so. Access point is just to glue the environment, two environments together. For that purpose, to facilitate the communication, the environment uh, is well enough there to facilitate it. So that is the basic service set. So in this basic service set, in this ad hoc environment, if you can see, these hosts would not be able to communicate with outside wired infrastructure, wired environment, or with another BSS. So within this BSS, these nodes can figure out what are the part of what are the nodes there which are the part of this BSS, and then after finding this they can contact those nodes. They can directly communicate with those nodes. In this infrastructure BSS also, this thing is well facilitated, but only because of this presence, the presence of access point. These nodes can contact other uh, basic service set. So two basic service set can can be can be can come together only through access point. So that is the part of the extended service set. So that's how we will form an architecture over network. So you can see these are all individual basic service sets, and these individual basic service sets are well accompanied by the access point. If there is no access point, that means these BSS would not be able to communicate with the outside environment. There is nothing to glue all these nodes together with the outside environment. So for that purpose, this access point is necessary. For any BSS to be the part of the extended service set, it should have an access point. And then these access points are directly communicated through the distribution system. And then this distribution system can be wired, can be wireless. So generally it is wired. So wired LAN we use to connect these access point, and then these access point can contact the outside server or the gateway through the access router. So that is the whole premise. So if you can see this under this BSS, if this node has to contact the node within this BSS, it doesn't require an access point. It can directly do so. Whereas if it does require to contact any other BSS host, in that situation, it do require this access point and router, and then finally that another access point that would properly enable one BSS node to connect to another BSS node. And everything when comes together, that broad network is called the extended service set. Now we know the importance of the MAC layer because we are using the common medium, the broadcast medium. Everyone can listen what you will share on the medium. So the chances of collision is more. In that situation, we do require a medium access protocol. Then the question comes that why can't we directly rely and use CSMA CD as we are using in case of the wired environment? Because in wired environment, detection is easier. While you are sending, you are receiving that signal which is coming as a collision signal. If that strength increase, because the collision would increase and would reflect in terms of the spikes on the channel. So once you will start receiving those spikes, high energy on the channel, that amounts to collision, and that confirms the collision. So in case of the wired environment, detection is easier, whereas uh, even in case of the wireless environment, because the host, if you will say, though these hosts rely on battery power, whereas in case of the wired environment, mostly those are all power backed. Whereas here in this case, in case of the wireless, it is battery backed or battery powered. So using transmitter and receiver at the exactly same time will lead to more consumption of the battery power. So it is generally avoided. Either you are transmitting or receiving. So both the things that you will start doing exactly at the same time, it would consume your battery more. So we generally avoid it. So that is also one of the reasons. There are several reasons we have discussed in past those reasons. This is also one of the reasons that why we can't directly rely on CSMA CD. And then there is a hidden terminal problem. So that's why detection is difficult there. So straight away we can't just rely on CSMA CD. So we have to come up with some other protocol which will allow us to avoid the collision at the very first instance. So how we will do it? So we have divided our data link layer into two parts. As you know, broadly we divide the data link layer into two parts. So for framing and all other operations, error control and these kind of operations, which are algorithmic in nature, which has to do something with processing. So all those things comes uh, and becomes the part of logical link control, LLC layer. So that LLC layer, you can see And then another one is the MAC protocol, which will allow you to access the medium first, because you can start using your physical layer only once you have an access over the medium. If you don't have an access over the medium, obviously prior to that you can't start using your physical layer, because physical layer means converting your data and encoding, modulation, all these things. So MAC layer is important. And why? Because here the medium is broadcast medium, and to avoid collision, first we should have an access over the medium, and we will rely on that kind of a protocol which would facilitate the avoidance of collision. So for that purpose, there is a layer distributed coordination function. This distribution coordination function uh, comes under, because here we are going to use CSMA, CA, and CSMA stands for Carrier Sense Multiple Access, and it's a contention based protocol. If you can go back and see the different types of MAC protocol, then one type is the contention based. Contention based means all the ones who are competing, they can compete, they can contest at the same time. Whereas in case of the point coordination function, PCF, it here also we will use one access mechanism that is polling based, that is centralized based. So there is a central authority there which has a right to poll first, and after getting the poll results, then it can schedule the nodes who will get an access for what time, for what duration, and in what sequence. So that protocol, if one has to use, then we will rely on point coordination function, PCF, that is centralized MAC protocol, polling based protocol. Whereas in case of the distributed coordination function, we rely on CSMACA, which is distributed in nature, as the name itself suggests, distributed coordination function, which is distributed in nature and generally work towards achieving the avoidance of collision. Generally we use this. So directly you can come over here, and if you want one layer of more security over the access protocol, then we can go for the polling based, and then you can go for the DCF operation. But generally we use, even in wireless environment, the distributed coordination function. Rarely we go for the point coordination function. At the physical layer, based on what kind of modulation mechanism you are using, we have different uh, standards at the physical layer, A, B, G, N, based on what kind of modulation approach you are using and the coding techniques and all. Now we will rely on uh, the CSMA-CA for our operation, for our DCF operation, distribution coordination function. So how it's going to happen? That there are n number of entities which are competing for the same medium. So how we will ensure distributedly? Because everyone is individual. There are n entities, but everyone is individual in itself and can contest for the channel. So there must be a contention comes out of this competition. So how we are going to resolve it? So we are going to resolve it using three ways. So first one is, there are three strategies. The first strategy is interframe space. So this is a sort of you can say that a sort of a randomness we want to introduce. So all the MAC protocol which are contention based, here the idea is to involve as much randomness as much possible. I mean, as much it is possible, put that much randomness in your protocol, so that everyone is relying on this randomness. So only one would eventually access the channel, because if the randomness is more, then obviously that interframe space time is will vary for everyone. So when it will vary for everyone, anyone for anyone out of these n entities, this interframe space time would be less. So wherever it would be less, that node would eventually hold the channel, would access the channel. So that is the whole idea. We will see that how it would happen, this interframe space. So how it's going to happen is, first, collisions are avoided by deferring transmission even if the channel is found idle. So what you will do, so let's suppose K is the number of attempt. So we will understand it with respect to one host which want to access the channel, the broadcast medium. So K is the number on the kth attempt. So initially it will start with the 0th attempt, the first time it is started. What we will check, we'll check that that node will check whether the channel is free or not. So here we will use some kind of a persistent mechanism, one persistent, any sort of a persistent mechanism we will use. So we will continuously check. So one persistent method we will use. So we will continuously sense it before. So not one persistent, just persistent method we will use. So continuously we will sense the channel. If it is busy, so we will continuously monitor it. If it is false, that means channel is not free, then we will once again check it if it is free or not. So we require here some carrier sensing mechanism. After sensing it using that persistency approach, if it is true, so once it is true, at that time, instantly we will not send the message. We'll wait for some random time. So what that random time is, that is, so we will wait for one interframe space. That is, IFS stands for interframe space. So it waits for a period of time called the interframe space, IFS, even though the channel may appear idle. When it is sensed, a distant station may have already started transmitting. Why we are doing it, why we are waiting for interframe space? So it is happening because you are not an individual in the environment. There are other nodes also. It may be possible that when you are sensing, you have sensed it idle, but other nodes have started it earlier, and when you sensed at that time, you were not able to receive the first bit of that frame, the first signal, the first wave. You will not be able to receive corresponding to that bit pattern, that frame. So in that situation, you would say that, okay, the environment is idle, the channel is idle, I can also go on. So in that situation, both of you will then collide. So for that purpose, what you will do, you will wait for more time, so that even though other would have started when you have sensed it, you would receive eventually, because even after IFS time, you will once again sense it. If it is idle, once again, you will then keep sensing it. So that is the idea. The distant station signal has not yet reached this station. The IFS time allows the front of the transmitted signal by the distant station to reach this station I have discussed. So what we will do after this IFS time, after waiting an IFS time, if the channel is still idle, the station can send, but it still needs to wait a time equal to the contention time. So after this IFS time, once it will be over, once again you will sense. Once you will sense, if you will find it busy, then obviously you will go back and continuously sense it again. There is no point. But in that situation, if once again it will be free even after IFS, what you will do, then you will go into the contention window, the contention time. And here also there is a sort of a randomness. We will see what kind of a randomness we will insert here also. So how we can play with this IFS and how it may be useful to set the priorities. You can see the IFS variable can also be used to prioritize station or frame types. For example, a station that is assigned a shorter IFS would have a higher priority. So that is the idea. Then after this IFS time, then the next option to insert a sort of a randomness is contention window. What is contention window? We have a time frame that we are calling a window. Now we will randomly divide this time slot into different slots. So there is a time window, there is a contention window we are saying. So like suppose there is a contention window of 1 minute or 2 minutes, whatever it is. So generally it is in seconds. So then this contention window, we will further subslot it. How we will subslot it? Based on binary exponential algorithm. So there we will make good use of this k. So suppose you are into your kth attempt. In that situation, you will randomly pick a value in between 0 to 2 raised to the power k minus 1. Once you will pick the random value, so then you have already slotted it, then you will use the rth slot. So what you will do, so initially based on this kth, first there is a total contention window. Now we have to sub slot it. How many slots we will form? We will frame how many slots? We will frame slot starting from the 0th number ending with 2 raised to the power k minus 1. That means in total 2 raised to the power k slot. So if the kth attempt is there, that the contention window is going to be divided into 2 raised to the power k slot, and then out of these 2 raised to the power k slot, we will pick a random value. We will pick a random value. That node will pick a random value, and then it will wait for that many random slot as well before sending the RTS packet. So here we will use the RTS and CTS packet. You know why we are using RTS and CTS? To handle hidden node and exposed node terminal problem. RTS and CTS. At least it will handle the hidden node problem. Though many of the time RTS and CTS are not suffice to handle the exposed node terminal problem, but at least it would, it would be able to handle the hidden terminal problem. So what we will do in contention window, you can see here in the contention window. So initially we are continuously sensing if the environment is busy, if the channel is busy, we'll continuously sense it. Once the channel found to be idle, after that we will randomly wait for IFS amount of. So for different nodes, it is different based on the priority. If you want to set a priority, if you want to give more priority to some other node, you can reduce this IFS. Once this IFS time will get over, once again you will sense. If you will find it idle, then what you have to do, you have to go into the contention window time frame. So this is the time frame, this is the contention time window. This window we have to break, we have to subslot this complete slot, the contention window slot, into subslot. And how we are going to subslot it? Based on the binary exponential. Binary exponential depends on the kth value. If the attempt is the kth attempt, so we will divide it into 2 raised to the power k slot. And once you will divide it, then you will pick a random value in between 0 to 2 raised to the power k minus 1. Whatever be the random value, then what we will do after each and every slot, we have to once again sense the medium. If the medium, then here is a twist. If the medium is free, then you will wait for another slot. If the medium you will find busy. So suppose if after the first slot, you have waited for the first slot, your random value is 5. Your random picked R value is 5. So there are how many slots? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 slots are there. So you have to wait for 1, 2, 3, 4, 5, 6. Means 5. You have to wait for 5 slots. Your value of R is 5. So what you will do, you will wait for this first slot. After each and every slot time, you have to once again sense the medium. If you will find it idle, then you will continue your counting. You will go for the next. Otherwise, if you will find your medium busy, you have to stop there as it is. So suppose if after the first slot time, first subslot time, the second slot time, you will find the medium busy. In that situation, you have to stop your timer. You have to stop the timer and you have to restart it when the channel is sensed as idle again. So in a way, you have to always wait uh, uh, for the random pick, for that random picked value, that is here in our case, that is r is equal to 5. What it will do, this gives priority to the station with the longest waiting time. So that is the second strategy. The idea is just the randomness. So using these two, we are putting a sort of a randomness, and that randomness we are reflecting in terms of the random amount of time each and every node will wait once it will find the channel idle. So different nodes, once they will find the channel idle, though they have found the channel idle exactly at the same time, but due to their different IFS and due to their different picked R value and due to their different K value, so in the end, eventually, the time will differ. So someone will have a reduced time, the combination of IFS and the contention window, that would be reduced, so that the first node will pick up the channel once, and other nodes will always then sense the channel as busy. So that is the whole idea. Then to the third one is an acknowledgement, which is necessary, because here in case of CSMA CD, why uh, we never require an acknowledgement? Because when we were sensing the response signal, that is the spikes, when we were receiving those spikes, so if we never detect any sort of unnatural spikes over the channel, then that itself confirms that our channel has never over our channel never got the collision. And because there we have never received any spike over the channel, we have never detected any unusual energy over the channel. So that itself confirmed that whatever we were sending has been received well at the destination site. So we never require, in case of the detection CSMA CD, we never require an explicit acknowledgement which comes from the destination site. But here it is not so. We do require an acknowledgement which comes, and a positive acknowledgement we require, we say that I have received, because here situation is different. We can't detect, we can't employ CSMA CD, so we do require an acknowledgement behavior. So once your destination receive each and everything, destination will respond back with an acknowledgement, which is necessary. Now what is the whole timeline? So we will see the exchange of this timeline. So suppose this is the source and this is the destination, and these are the nearby nodes. So these are the nearby nodes. So all these nodes are in a way competing for the common channel, that is the broadcast channel, the wireless channel. So we are making good use of RTS and CTS. So how we will do it? So before sending a frame, before sending this data, this one is the source and this is the destination. So before sending a frame, the source station sends the medium by checking the energy level at the carrier frequency. That means it will sense it for idle or whether it is busy. So channel uses a persistent strategy with back off until the channel is idle. So that is this mechanism. So channel will, so each and every host will do this kind of thing before getting hold of the channel, before accessing the channel. After the station is found to be idle, so once this stage will be over, and once after the Rth slot, once again your channel is idle, then your source node has to wait for DIFS amount of time. That is well established time. So initially each and every node knows what is DIFS time. So it has to wait for this DIFS time. It is just to ensure once again. So DIFS time, whenever we are inserting an idleness in the behavior of any node through this interframe spacing time. So it is just to insert a sort of a randomness so that if any eventually has to happen, would happen during this time. If anything is not happening, that means nothing will happen later. So for that purpose, once again, the source will wait for the DIFS amount of time, and then will then send the RTS time. In this RTS time, one more important thing, RTS is the request to send, that this source wants to communicate with this destination. In our protocol, we have seen on the whole RTS in detail and CTS. So after this DIFS time, source will share it with RTS. Destination will wait for short interframe space, SIFS, short interframe space. That is also well-defined time for a particular node. Then after this SIFS, this destination node will share CTS that okay, I'm ready, so I'm clear. So you're clear to send. You can send it. Then once source will receive this CTS, now through this CTS, other node will also come to know that we don't have to communicate with this destination node, otherwise there will be a collision. So in this way, we can avoid the exposed terminal problem. Now the source will wait for another DFS time and then start communicating its frame. So that is the data. Now once destination will be with its data, it received all the data, then after SIFS time, it will acknowledge it. So after that, that acknowledgement will be there. So before this DFS time, this mechanism is there which involve some sort of a persistent approach, then this interframe space, then the contention window. Within contention window, the idea of the contention window is to subslot the contention window using binary exponential. After this binary